All right. Well, while there's no one here, mess around with my setup for a minute. Gonna have to apologize. I've not uploaded the video from the last session. Very bad of me. I will have to do that tonight, actually, or else I will forget forever. All right, so here I am with auto negotiation. So we're reading about Ethernet. We have finally gotten to the auto negotiation part of this book, which is kind of exciting for me. Because auto negotiation always seemed like magic a little bit to me. So I'm excited to see kind of how it works. And I just realized that the most important thing hasn't happened, which is, there we go. Light up my little Art of Network Engineering logo there. Yeah, all right, cool. Good to go. All right, so I'm just going to start back a little ways from where I ended last time as a review for myself and anyone else who doesn't remember or doesn't care enough to remember. That's fine too. We're going to go back over it anyway. So here we are. Basic concepts of auto negotiation. The auto negotiation system makes it possible for Ethernet stations to exchange information about their capabilities over a link segment. This in turn allows the stations to perform automatic configuration to achieve the best possible mode of operation over that link. At a minimum, auto negotiation can provide automatic speed matching for Ethernet devices at each end of a twisted pair link. By using this mechanism, an Ethernet-equipped computer can automatically take advantage of the highest speed offered by a multi-speed Ethernet switchboard. The auto negotiation standard includes automatic detection of more than just the speeds of the interfaces at each end of the link. An Ethernet switch capable of supporting full duplex operation on its ports can advertise that fact using auto negotiation. If a station that also supports full duplex operation is connected to the switch, then the station and the switch port can automatically configure themselves to use the full duplex mode over the link. However, the auto negotiation system does not perform any cable tests, such as detection of the number of wire pairs or any signal performance tests. So if it doesn't work, it doesn't work. And you got to start at layer 1, right? As you'll see later in this chapter, well, I guess we're still at layer 1, but you know what I mean. Auto negotiation was designed to be extensible and to support the negotiation and configuration of multiple modes of operation and other Ethernet features. Automatic configuration makes it possible for vendors to build twisted pair Ethernet interfaces that can automatically support several speeds, so that Ethernet switches now support multiple Ethernet speeds on their twisted pair ports, as do the twisted pair network interfaces in computers. Depending on the cost of a switch, switch ports may support either 10-100 or 10-100-1000 megabits per second operation. If a switch port supports 10 gig Ethernet, then it typically will support 100, 1000, 10,000 megabits per second operation. All right. Operation of the auto negotiation system includes the following basic concepts. So the first one is auto negotiation operates over link segments. Auto negotiation is designed to work only over a link segment media system. A link segment can only have 2 devices connected to it, one at each end. Okay, so device to device, that's a segment. That device to another device, that is also a segment. So we can't have more than one device auto negotiating on that same connection, right? When a device is turned on, this next one. So that was auto negotiation can only operate over link segments. That is 2 devices on the link. That's it. Auto negotiation occurs at link initialization is our next concept. So when a device is turned on or the Ethernet cable is connected, the link is initialized by the Ethernet devices at each end of the link. Hi, the real Erikarn, welcome. Thanks for joining. I don't know if you know what this is or if you just sort of randomly found the stream, but welcome. Thank you for coming. This is the most boring stream that exists. Okay. Yeah, so device is turned on. Everybody is coming up. That Ethernet auto negotiation is going to start happening right away. Well, more or less. I gotta be careful with statements like immediately or right away or guarantee or absolutely. So auto negotiation and link initialization occur only once prior to any data being sent over the link. Once the link characteristics are set, they remain the same as long as the link is up. Which makes sense. Why would they change? It's not like routing where you're like, oh, hey, Adrian. Adrian. Wait, which Adrian is this? I'm so sorry. I know several Adrians. Welcome. It's really good to have you here. I'm really glad you're here, whichever Adrian you are that I know. Okay. If I work with you, I'm so sorry. I'm so sorry. Oh shit, Adrian. Okay. You're the one that I asked about hardware on Twitter. Good. So we don't work together and I don't have to apologize too much to you. You already know how weird I am. This is good. Okay. Hey, thanks for coming. Adrian knows so much more than I do about different hardware things, so please feel free, Adrian, to shoot comments in as you have them, because you know a lot. Oof. All right, where was I? Okay, so we have our first two concepts basically so far. Auto negotiation is only going to operate over segments. That's device A and device B connected to each other, nobody else. It also happens at link initialization, and as long as that link is up, auto negotiation the characteristics of that link stay the same. And then our third concept, twisted pair auto negotiation uses its own signaling system. So this is a bit more information here. Although each twisted pair Ethernet media system has a particular method of sending signals over the cable, the twisted pair auto negotiation system uses its own independent signaling system designed to operate over any twisted pair cabling that can be used to support Ethernet. If auto negotiation cannot establish a common mode of operation, the link will not come up. If there's no common technology detected at each end of the link, then the auto negotiation protocol will not allow communication. In this case, the switchboard or network interface card, God, I hate when they trick me into reading that out loud. It's NIC. Just shorten it to NIC. I think they just keep saying network interface card no matter how many times they shorten it after that. Oh my God. Okay. So if auto negotiation can't detect a common technology on either side of the link, it's just not going to allow communication, which means that the switch port or the NIC won't be functional. This is the same situation that occurs when two incompatible Ethernet devices that don't support auto negotiation are connected over a link. The two different systems can't communicate, and the link will not come up. Okay, so all that makes sense. It's not really that hard to grasp. If it doesn't work, it doesn't work. End of story. We have to have a common thing on either end. When describing the operation of auto negotiation, the device at the opposite end of a link from a local device is called the link partner. Using the auto negotiation protocol, each device advertises its capabilities to the link partner at the other end of the link. The protocol then selects the highest common denominator between the devices at each end of the link. And here we go. We have a little diagram below. So we're assuming that okay, computer A right here only supports 10 base T, right? Or 100 operation. And then computer B is only going to support 1000 base T, or that's 1 gig over copper Ethernet, right? So we have like a higher standard. Okay, so this, oh, let's see, I'm sorry. Computer B only supports 1000. Yeah, okay. So computer B, even though it is labeled 100 base T, which just confused me for a moment, it's actually 1000 base T is really what this should be. So we have 10 base T up here and 1000 base T down here. And then we've got our switch that they're both connected to, right? So with auto negotiation, both these computers with their different like support operation support, like their different speeds, they can both connect to the same switch because this switch is able to support 10, 100, and 1000 base T. With auto negotiation, both of these computers can negotiate individually with the switch port that's attached on the other end. And set up their links to be what they need them to be, right? So it'll be 10 base T on this link and 1,000 base T over here. Easy. All right, auto negotiation signaling. All right, the auto negotiation communication method for twisted pair Ethernet is based on the link integrity test pulse, which was first developed for use in 10 base T media system, but the 10 base T link pulse was designed to protect a 10 megabit per second twisted pair Ethernet link segment from an undetected failure in the two pairs of wires used to carry signals over the segment. Okay, so to help the Ethernet device at each end of the link avoid the problem of an undetected failure, 10 base T transceivers transmit link pulses when there's no data being transmitted. Okay, so I think I probably said this in the last stream, but I'm just going to say it again anyway. But I've seen situations in production when, we had a link, nothing configured. It's up because it's administratively up on both ends, and that's it. But so there's no data flowing is really what I'm saying, right? I've seen situations where there's no data flowing for sure between those two, and by data I mean like traffic, right? Like data traffic, not just like anything, but data traffic specifically. There's nothing being routed over this link. It's not in use technically by anything significant. So I've seen situations where a link like that will have errors incrementing on it, like FCS errors. And it's like, okay, I remember being confused as a new network engineer, like why, if there's no traffic going over it, why the hell would it be incrementing errors? This doesn't make any sense to me, and I don't get it. And it turns out, that's how I learned from another experienced network engineer that actually there is technically some data going over that link. It's just not the traffic that you normally would see or expect to go over it when you're like routing, like if you're an ISP, which I was, customer traffic, for example, was not going over that link. And I just assumed that no signaling at all was going over the link when there's no data traffic, but that is not true. We actually have these little keep alives happening, and that is a feature of Ethernet. So our 10 base T in the situation that they're giving us, but also it can be like 1,000 base T and so on. Those transceivers are going to transmit little link pulses when there's no data being transmitted. So continual reception of either a data signal or a link pulse. So when that customer traffic is not flowing over that link, then we're sending link pulses still back and forth to make sure we know, okay, this link is up. That assures that the interfaces at each end of the link know that the link is working correctly and they don't go down. Okay, and then our little lemur tells us the signaling methods used in faster Ethernet systems result in a continual stream of signals even when there's no data being sent, which means that the link pulse used in the 10 megabit per second system is not needed to detect a link failure on faster systems. Okay. The auto negotiation system uses a burst of the normal link pulse, or NLP signal, which is called a fast link pulse. So I guess there's a normal link pulse, and NLP that I guess in slower systems or non-auto negotiate is used as a keep alive type signal. But with auto negotiation, we're using a faster version of that, a burst of that. So it's an FLP. The FLP signals are used to carry auto negotiation information between devices at each end of the twisted pair link. The auto negotiation FLP signals are specified for transmission over the set of Ethernet twisted pair media systems, including 10 base T, 100 base TX, 100 base T4, 100 base T2, 1000 base T, and 10 gigabase T. Of these media types, the 10 base T, 100 base TX, and 1000 base T systems are very widely used. The 10 gigabase, I want to say gigabase. I don't know if it makes more sense to say 10G base T, whatever. 10G base T system is often used in data centers and other environments that require high-speed performance. I just want to look this up real quick. Yeah, okay. It's exactly what I thought. It's just 10 gig Ethernet. That's it. Is it so copper Ethernet, I guess. Yeah. Oh no. Maybe it's not specifically for copper. No, it is. Okay. This is a long rabbit hole I was going down. I'm sorry. Um, yeah, you know what? I don't know. I think 10G base T is probably just talking about the copper, and the fiber cabling, it looks like might actually be, yeah, okay. So fiber would be like 10 gigabase SR, 10G base LR, ER, LX4, and then we've got WAN versions of that as well. So 10G base T is specifically copper. Sorry, I just wanted to satisfy my curiosity there. Okay. 10G base T system is often used in data centers and other environments that require high speed performance. I love how they say this. This book is from 2014. We're probably at 40 to 100 gigabit at least in data centers, probably 200 gigabit in, big ISP backbones and more. Anyway, equipment used on the 100 base T2 standard was never built or sold, and although 100 base T4 equipment made it into the marketplace, it too is no longer sold and is rarely found in use. Sad. Hello, Sparkling Citrus. Welcome. Little robot face. I love those little robot emojis. All right, FLP burst operation. Let's talk about that. When a link with auto negotiation support at both ends is initialized, the devices at each end perform auto negotiation by each sending FLP burst to their link partner. Okay, so we come up, our devices come up, we have auto negotiation enabled, and bam, we send a burst to each other. Link initialization can occur when a link is completed by connecting with a patch cable, when one or both ports of a complete link are manually enabled via their management interface, or when one or both devices at each end of the link are powered on. Hey, awesome, Sparkling Citrus. I'm glad you managed to catch me live. I've been really trying to stick to the very sparse but regular schedule that I've set, which is Mondays at, I think I had it at 6:30 PST. I was a little bit late today, but it's tough, I should probably make it later, but I was doing around this time in Central Time when I was in Central Time a few months ago, and I just didn't want to change it too much for people. Let's see. So link initialization can occur in a bunch of different ways, basically. So as long as the link has come up in some way, that's initialization of auto negotiation as well. All right, and of course, true to form, we have a diagram that we can't see that's being described here. Two link partners, an Ethernet station and a switch port sending FLP bursts to one another over the link. The FLP burst consists of 33 short pulses, with each pulse 100 nanoseconds wide. The timing between successive FLP bursts is the same as the timing between NLPs. So here we have our little diagram. So FLP is from link partner A right here, our desktop, to link partner B. Boom. The last link pulse in a burst of fast link pulses is timed so as to appear to older 10 base T equipment as a normal 10 base T link integrity test signal, and the rest of the FLPs are simply ignored by older equipment. This timing convinces a 10 base T device without auto negotiation that it's receiving an NLP, providing backward compatibility with older 10 base T equipment that doesn't support auto negotiation. That's kind of cool. I like knowing the details of that. The last link pulse in our burst of fast link pulses is timed so that it looks like what the 10 base T shit is used to looking for. Okay, so we have yet again, another figure that we can't see at the moment, but it's showing the burst of FLP signals used to send information about device capabilities. So that's here. Okay, oh, cute. Boop, 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 boop. Of the 33 pulse positions in a fast link pulse burst, wow, that just like went through my brain in like a very weird way. Of the 33 pulse positions in a fast link pulse burst, the 17 odd-numbered pulse positions each contain a link pulse. The word pulse has been used so many times in this sentence that I think I've forgotten what it means. Fuck, and now I've lost track. Of the 33, we have 33 pulse positions in a fast link pulse burst, an FLP burst. The 17 odd-numbered pulse positions each contain a link pulse that represents clock information. Why did they phrase it that way? That's horrible. This is horrible wording. The 17 odd-numbered pulse positions each contain a link pulse that represents clock information. Okay, so you have 33 pulse positions, whatever the fuck that is, in your fast link, in your burst of FLPs, okay? There's the 17 that are odd numbered have clock information in them, basically. So every other pulse position in your burst has clock information. The 16 even numbered pulse positions represent data. So every other like FLP sent in your burst is clock information and then data, and then clock information and then data. The presence of a pulse in an even numbered pulse position represents a logical 1. Okay, so the even numbered pulse position means logical 1, and the absence of a pulse represents a logical 0. The encoding scheme is used to transmit the 16-bit link code words or messages that contain the information used by the auto negotiation protocol. This is fucking wild, all right? This is exactly the amount of like depth that I wanted to get to, and my brain's just not wrapping around it, which is normal, but whatever. I'm gonna go back over this paragraph one more time so that it sinks in. Okay, so we have a burst of signals that's sent, right? And why is this sent again? It's just how auto negotiation works, right? Yeah. We use it for initialization. Specifically for initialization, I think. When a link with auto negotiation support at both ends is initialized, we perform auto negotiation by sending FLP bursts to our link partner. I don't know if that's saying that this only happens at initialization or that's what's happening all during auto negotiation. Whenever the link is up, it just starts when it's initialized. I don't really actually know if they're saying it only happens then or it always happens. But so in our example, we have a bunch of FLP bursts, and each of them consists of 33 short pulses, each of them 100 nanoseconds wide. Okay, so that's a little bit of information about, I guess, what they look like. Yeah, okay. And then we have backwards compatibility with 10 base T. All right, so of the 33 pulse positions, I hate that phrase. So I guess, so we're talking about 30, in FLP bursts is 33 short pulses all at once, I guess, really fast, right? So when they say pulse positions, we're talking about just like a short pulse rather than the burst of, fast link pulse. I don't know. I'm trying to figure this out. So Of the 33 brief little pulses that make up a fast link pulse burst, okay, so we have 33 pulses. Start with number 1 that has clock information. Number 2 is going to have data. Number 3 is going to have clock information. Number 4 has data, and so on and so forth. So the presence of a pulse in an even numbered pulse position, or rather, okay, we have 33 places for pulses to be. If we don't send a pulse, that's a logical 0. If we do, that's a logical 1. Oh my god, I think I've understood it. Let's look at figure, yeah, we'll look at the figure, don't worry. Okay, here's figure 5.2 if you missed it, sorry. So we've got, it's just showing like 2 devices connected, and it's not really showing a whole lot, right? Like this doesn't really help us. It's just like, oh yeah, you know, A to B is connected and we're sending bursts back and forth. That's all it means. But we should look at 5-3. So this is 5-3. Interesting. Yeah, okay, so our bursts, I guess, are separated here, so we can see like this is maybe one first burst, right? And here's the second burst, and so on and so forth. Shut up, Adobe. Okay, 2 milliseconds across. Interesting. So it's showing, I guess, the difference between like FLP bursts are really, really compact and quick, right? We've got a lot in this 2 milliseconds that keeps going. The NLPs are the shorter ones. Sorry, the longer lasting ones with less data in them, I guess. You can see how far apart they are, right? So we have like separate one here and a separate one here, and we're, instead of 2 milliseconds between them, we have 16 plus or minus 8 milliseconds. So 16 to like 24 milliseconds in between. Okay, FLPs are going both ways is what Adrian's saying. Okay, cool. So the NLP is how it looks with no auto negotiation on 10 base T. Right. Okay. So we're talking no auto negotiation here, the NLPs, compared to this is what it looks like when auto negotiation is happening. FLP bursts. Bam. Okay. Okay. Yeah. All right. And we're clarifying that this is purely just the link is up. It doesn't have anything to do with like data's being sent right now. It's just the link initializing. When link initialization occurs, the auto negotiation protocol will exchange as many 16-bit messages as are needed. However, many media systems can complete the negotiation in the first message, also called the base page message, shown in figure 5-4, which we actually can see. Okay. All right, so this is the format of an auto negotiation base page message. Cool. The 16 bits are all labeled. So our first bit is D0. Then we have D1, D2, so on and so forth through D15. So we have 16 bits. Bits D0 through D4 are used as a selector field. So these guys right here. Yeah. Which identifies the type of LAN technology in use, allowing the auto negotiation protocol to be extended to other LAN technologies in the future. For Ethernet, the S0 position of the selector field is set to 1, and all other selector field positions are set to 0. Okay, so we want to indicate that we're using Ethernet in the selector field. So we have a 1 at D0 and then 0, 0, 0, 0 after that. The 8-bit field from D5 through D12 of the base page message is called the technology ability field. You see it right here. Okay. The bits in this field are identified as A0 through A7 and are used to indicate support for various technologies, as shown in the next table. If a device supports one or more of these capabilities, it sets the corresponding bits to 1. An auto-negotiating device may use these bits to advertise all of its capabilities in a single base page message. All right, cool. So bits in a certain position mean it supports that technology. Boom, we're done. All right, cool. So if A0 in or position D5, if this guy is set to 1, then it means that we support 10 base T. If A1 is set to 1, we support full duplex 10 base T. And if D7 is indicated with a 1, we support 100 base TX. D8 is our full duplex 100 base T. D9 is 100 base T4. D10, pause operation for full duplex links, which we've already gone over. D11 means asymmetric pause operation for full duplex links, and D12 is reserved for something in the future. Bit D13 of the base page message is called the remote fault bit. So that is this guy, just after the technology ability field. This bit may be sent by the remote link partner to indicate that the partner has detected a fault at the remote end. For example, if computer B in 5-1, scroll up. Oh my God. There we go. Wait, is this what it's talking about? Oh, I'm sorry. We're talking about 5-1. My bad. Thought I had to scroll all the way up. Oh, this was a while ago. God damn it. Okay, this is computer B with our 1,000 base T, I think. Support. God, I'm gonna have to scroll all the way down. Keep going. Keep going. There we go. If computer B in that situation detected a failure of the incoming signaling, it could set the RF bit to 1 to signal that the switch, to signal to the switch that the receive side of the link to the computer had failed. I love knowing exactly how these things are communicated between devices. It always comes down to a bit being flipped, like basically, or like being, purposely flipped. So D13 is where we indicate if we saw a remote fault. D14 is our ACK bit used to acknowledge receipt of the 16-bit message. Negotiation messages are repeatedly sent until the link partner acknowledges them, completing the auto-negotiation process for that page or message. Okay, so we do need ACKs in auto-negotiation. It's very interesting. Ooh, QoS. Sparkling Citrus is offering to talk QoS. Ugh, I hate QoS so much. Aw, thank you. Thank you for the nice things you said, Sparkling Citrus. I also love your username. It's awesome. I don't know who you are on Twitter. Are you Sparkling Citrus on Twitter? I only know people by Twitter handles now. It's a little stupid, but that's my life at the moment. Thank you though. Very nice. All right, I think we're down. We've gone through 16 bits, and that's all it is. So we need ACKs with auto negotiation. After 3 consecutive messages received that contain identical information, the link partner sends an ACK. This helps to ensure that the auto negotiation process receives messages correctly, even if some bit errors are encountered during the negotiation process. The final bit in the base page message, D15. Oh. Stupid. D14 is the 15th bit, not the 16th. Okay, so D13 is our remote fault bit, D14 is our ACK bit, and then our final bit, D15, is used to signal the next page. Capabilities that are not listed in the base page technology ability field may be advertised in 1 or more additional next page messages. The next page protocol provides the ability to send vendor-specific commands or any new configuration commands that may be required as Ethernet evolves. Interesting. For example, both the 1000 base T and 10 G base T media systems use the next page protocol to communicate and configure capabilities over the link. That's fascinating. What kind of capabilities? If a device implements this protocol and wishes to send a next page message, it sets the NP bit to a value of 1. Okay. The next page protocol consists of a 2-message sequence. The message page indicates the number and type of unformatted pages to follow. I'm going to go back over that because my brain didn't absorb it. If a device implements this protocol and wishes to send a next page message, it sets the NP bit, so D15, to a value of 1. The next page protocol consists of a 2-message sequence. The message page indicates the number and type of unformatted pages to follow. I don't know what we're talking about here, but I'm trying to get through it. The unformatted pages contain the data being exchanged between the link partners. 2 acknowledgement messages are provided as part of the next page exchange. The first acknowledges receipt of the messages, and the second indicates whether the receiver was able to act upon the information or perform the task defined in the next page message. I have to talk about something embarrassing that happened to me today real quick. It has nothing to do with this. It's just clouding my mind. So somebody sent an email about what an IP address should be, and the IP address had the number 45 in it. And then someone else confirmed it, and they were like, oh yeah, it should have that in it, except their IP address instead of 45 had 145 in it. And then I, with 4 years of network engineering experience, replied to that email thread and went, so should it be a .45 or a .145? And I wanted to die. As soon as I sent it, I knew it was a mistake. I sent it and then I realized what I did and I wanted to die. Okay, it's out. It's gone. I feel better. It's over. I'm going to edit that out. All right. I'm zen again. Aw. Sparkling citrus. I think we need more girls in tech, so it's refreshing. Oh, thank you. Yeah, I got it. Thank you very much, Sparkling Citrus, for saying that. We do need more women in tech. And I don't know what to do about that anymore. You know, I've like tried to figure it out. It's hard. It's hard. I think just culturally, like nobody wants to hear this, but I think like there's things you can do in your workplace to make women not hate it there. Like that's cool. But I also think that like just culturally, in not everywhere, but in many places, we still like subconsciously or more than that, consciously hammer home to women that like our jobs are to be pretty and look good and shoot babies out. And that's it. Like that's, I mean, and there's a lot of people even today who are in tech who think that women are like super nurturing by nature, and that means that we can't do tech. And that's just complete and utter nonsense. I don't know what the fuck being nurturing has anything to do with your job, to be honest. I mean, like it has things to do with your personality and what you like to do for a job, but like tech is not just like sitting in a corner. Like, am I sitting? Okay, I know I'm sitting in a room that's dark, but like, you know, when I'm at work, I'm not fucking sitting in a corner coding all day. Like, I know there's some jobs that are that, but that's not usually what it all is, right? Like, there's plenty of room for people of all personality types and genders and whatever to like be in tech. I don't really understand that. Anyway, we need to stop fucking telling people outright and subtly in little microaggressions that like math is for boys and tech is for boys and boys like wrenches. Like stop giving your like little boys, stop only giving little boys like wrenches and tools to play with. Fuck you. Stop it. Stop it. I don't care who gave your baby that gift. It was if it was the in-laws or what. Stop it. Stop it. Give your little girls little baby tools to play with too. Like that is that kind of shit, right? All right, I'm off my soapbox. I'm sorry. It's not enough. It's not enough to just like once a woman has grown to like 22 years old and suddenly we just like inundate her with like, you should go into tech and like, have you ever thought about programming, girl power, tech? Like, fuck you. No, you should have done that when I was like 2 years old, right? Because I didn't know anything. Like you just shot all these messages out at me. Like, you know, you gave me dolls to play with and Barbies, and like you didn't even give me the option. Like you didn't even give me, I didn't know what I wanted. I was a fucking 2-year-old. Give me a fucking truck. Let me play with a fucking truck. Or let me like try to take things apart and put them back together. Or why didn't you, when I was 10 years old, why didn't you offer to like help me build a PC? Because I liked playing games. Why didn't you like offer to show me how to build a thing that would let me play the game? Like, show me something as a little girl, right? Like, don't just like find a 22-year-old woman and be like, get into tech. Like, fuck you. No, it's too late by then, right? It's not too late, but like, it's much, much fucking harder. I got into tech at 28. So, like, do better. All right, I'm done. Once the stations have completed the auto negotiation process, additional bursts of FLPs will not be sent over the link. Okay, so we have our answer. This happens at initialization and like advertising of our abilities. The auto negotiation system continuously monitors the link status and will notice if a link goes down and comes back up, e.g., if a link outage is caused by like disconnecting it, or, you know, I guess if a device goes down on one end, that'll also do it. Once a link comes back up, the auto negotiation process will start again from the beginning. Cool. A girl who eats, sleeps, and breathes Ethernet. How does this happen? You know how it happens? Well, okay, wait. I don't eat, breathe, and sleep Ethernet. I'm trying to, but like I only do it once a week, right? I wish I could do it more, but like it doesn't pay the bills, so here I am. I'm learning Ethernet partially for work and partially because I think it's really fascinating, and I've taken it for granted like really badly my whole networking career. Um, and yeah, demystifying it is fun. Um, this happens because I don't know, work and stuff. Finding a technology to like talk about, right? But there are a lot of women out there. There are actually a significant number of like female network engineers on Twitter, and I didn't know about them, and I feel really bad for not knowing about them, but now I do. Shout out to Emirage. I think that's how you say her Twitter handle. Emirage, Emirage. She's awesome and adorable, and she makes cute memes, which I can definitely relate to about networking. She just got her first network engineering job. I think she was like a social worker for a while, and now she's a network engineer. Fucking yeah. Okay. Auto negotiation operation. You're gonna listen to me talk about this while I have cheese in my mouth. Auto negotiation protocol contains a set of priorities used by the link partners on a given link to select their highest common set of abilities. When two auto negotiation devices with multiple capabilities are connected, they find their highest common denominator based on the priority table specified in the standard. Okay. Interesting. The priority is assigned by technology type and is not based on the bit ordering in the technology ability field of the base page message. Not assigned by technology type, not based on the bit ordering in the technology ability field of the base page message. So not based on scroll. Here we go. Not based on the order of the bits here. It's interesting to me that they're telling me this as if I was worried about that, or that's what I thought. I don't know. Okay. So not based on the order of the bits here. And it's also not based on the type of technology being used either. What is it based on? The priorities defined in the standard for twisted pair auto negotiation are listed in this table, ranking from highest to lowest priority. Okay, so it tells us what the priority is assigned is not based on, but it doesn't tell us what it is based on. So does that mean it's just like they just sort of decided? I don't know. Okay, so here's our resolution table, priority resolution table. Full duplex 10 gigabase T, which is 20 gigs, right? Okay, I guess they're saying, wait, priority table. Maximum aggregate data transfer rate. Why do we have a close parentheses here? Okay, so we're ranked, let's see. Okay, so we're talking about finding the highest common denominator between two auto-negotiating ends of a link. And the highest common denominator is determined by priority, and this is the standards priority table, ranked from highest to lowest. So it's basically we're just going down this list, and whichever one from top to bottom is first common between the two, that is the one that we're going to go with. So we have full duplex 10 gigabase T, which means a max data transfer rate of 20 gig a second. Next down is full duplex 1000 base T, max transfer rate 2 gig a second. Then we have 1000 base T, 1 gig. Full duplex 100 base T2, 200 megs. Full duplex 100 base TX, 200 megs. Again, 100 base T2, 100 base T4, 100 base TX, those are all 100 megs. Full duplex 10 base T is 20 megs, and 10 base T itself, half duplex, is 10 megs. All right, so we are very concerned. I bet we have some more things to add to this list, to be quite honest, since this book came out in 2014, and it is now 2022. So I'm sure we have some other ones, but this is where we're at in 2014. The reasoning behind priority resolution is described in the following excerpt from the standard. Yay, standard reading. This is IEEE Standard 802.3-2012, Annex 28B.3, Section 2, page 731, in case anyone is interested. The rationale for this hierarchy is straightforward, they say. 10 base T is the lowest common denominator and therefore has the lowest priority. Full duplex solutions are always higher in priority than their half duplex counterparts. That makes sense. 1000 base T has a higher priority than 100 megabit per second technologies. 100 base T2 is ahead of 100 base TX and 100 base T4 because 100 base T2 runs across a broader spectrum of copper cabling and can support a wider base of configurations. 100 base T4 is ahead of 100 base TX because 100 base T4 runs across a broader spectrum of copper cabling than 100 base TX. The relative order of the technology specified herein shall not be changed. As each new technology is added, it shall be inserted into its appropriate place in the list, shifting technologies of lesser priority lower in priority. If a vendor-specific technology is implemented, the priority of all IEEE 802.3 standard technologies shall be maintained with the vendor-specific technology inserted at any appropriate priority location. Okay, so that was a lot of words just basically saying, all right, the shittier ones are lower priority. Like, whatever. All right, cool. The full duplex aggregate data transfer rates in the table reflect the fact that full duplex operation allows simultaneous two-way transmission, resulting in a maximum aggregate transfer rate for full duplex operation that's twice the half duplex transmission rate. All IEEE twisted pair Ethernet technologies that are listed in the standard are in Table 5-2, whether or not they've been successful in the marketplace, i.e., 100 base T2 and T4. I think they were listed as not being super successful in the marketplace. This has to be a typo right here because it's saying this lemur is telling me that 1000 base T half duplex. Oh, half duplex. Okay, never mind. This makes sense. Anything half duplex should not do well these days. There's no reason to have half duplex that I know of. The 1000 base T half duplex, 1000 base T2, and 1000 base T4 media systems were not widely deployed or were never sold. Okay. Oh yeah, okay. So for anyone coming in new, this is actually a book, a PDF of a book that I'm reading. It is called, well, fuck it. What page are we on? It's about that time when I need to remind people where we are. Okay, we're on page 73. So this book is called, it is called Ethernet oh my god, scroll. It's called Ethernet the Definitive Guide. This is the book. I have bought it. It was legal. No one can get mad at me except for O'Reilly, maybe, because I'm literally reading their book out loud. I'm sorry. All right, back to 73. Okay. Oh, this this is a big page with no tables or anything interesting, just a lot of text. The physical layer is my least favorite topic. It was my least favorite topic, and then I had to work at a place where it's gotta be real important. So here I am, reading about Ethernet on a Monday night for fun. Okay. If auto-negotiating devices at both ends of the link can support full duplex operation, then they will automatically configure themselves to use full duplex. I feel like this is just an exercise in common sense, but whatever. The priority list in 5-2 shows that if both devices on the link advertise they can support 10 base T and 100 base TX, for example, then the auto-negotiation protocol in the link partners will connect using the 100 base TX mode instead of 10 base T, because 10 base T is shitty and why would anyone use it? If both link partners also advertise full duplex capability, then the 100 base TX full duplex mode will be selected. If both link partners support the use of pause frames for Ethernet flow control, and if the link is enabled for full duplex operation, then pause operation will also be enabled at each end of the link. Okay, that's cool. I, before this book, did not know pause operation was a thing at all, so good to know. Pause operation, by the way, if you weren't here for the last one, is a feature of Ethernet flow control. It's literally like, oh, hey, stop sending frames for a second type of communication. Pause operation can be configured via auto negotiation over twisted pair or, twisted pair or gigabit Ethernet fiber optic segments, but only if the segments are using full duplex. Because the use of pause is independent of data rate or link technology, it's not included in the priority resolution table. Okay. The pause flow control system is described in detail in chapter 4. Okay, we already went through that. If there's no common technology detected at either end of the link, then the auto negotiation protocol will not successfully complete and the link will not come up. For example, if a device that only supports 10 base T is connected to a port on a switch that's configured to only support 100 base TX, then no connection will be established on that link. This outcome is unlikely on twisted pair segments that are configured to allow auto negotiation, as the vast majority of twisted pair Ethernet switches and NICs support multiple speed operation on their ports. Switch ports commonly support 3 twisted pair media speeds. We either have 10, 100, or 1000 megabits per second, which is very common, or the slightly less common 100,000, 10,000 megabits per second on switches that support the twisted pair version of 10 gig Ethernet or 10 G base T. How are we doing? Is everyone asleep yet? I believe we're probably asleep, and that's cool. I'm just reading this footnote here. Orthogonal. I love that word. It's a good word. It's so weird. The setting of these bits indicates the availability of additional DT. All right, I don't want to read this footnote anymore. It's boring. Ooh, Network Warrior. Network Warrior is a good book, and I've not gotten through all of it, and I feel such shame for having not done that. Maybe I'll do that next when I finish this book in 20 years. Okay, parallel detection. I'm already tired, man. Been at this for just about an hour now. It's probably time to quit soon. Hey! But I have a first time chat from viewer. Now I have to keep going. Hi, welcome to the most boring stream in the history of ever. I'm reading out of a book about Ethernet. So welcome. I don't know if anybody here even cares or if everybody's been here the whole time. I don't really understand how viewership works on Twitch, but for anybody who doesn't know what the fuck is going on, I'm a network engineer. I'm learning about Ethernet because of reasons. Ethernet is like the most common technology by far for connecting shit. Computers and routers and switches and the internet and all that crap. So I'm learning more about it. So this means we're basically going through the physical layer. A lot of the physical layer, blah, blah. Yeah, it's basically the physical layer. I'm trying to think of part. I mean, we have layer 2, the data link layer, involved as well. But a lot of it is physical, electrical signaling, talking about twisted pair shit, Right now we're talking about auto-negotiation, which is a feature of Ethernet now. It wasn't originally, but it is now, and it's really, really good for most circumstances. Am I filling a needed niche on Twitch by reading out of a book about Ethernet? Fan-fucking-tastic, because I'm going to keep doing it until someone tries to sue me for... O'Reilly, please don't sue me. I like your books. They're way less full of, like... Hang on. There we go. They're way less full of problems than a certain publishing company we all know and love, Cisco Press. Okay, yeah, we don't have much computer networking on Twitch, but man, this is like the most boring computer networking because it's the studying part. I'm not even studying for an exam right now. I'm just fucking reading out of a book. But yeah, when you do your CCNA shit, they talk about Ethernet, and they do go through like, this is the Ethernet frame, and like this is a feature of Ethernet, but they don't like go super deep into Ethernet, understandably. As a first-time network engineer, when I was learning CCNA stuff, I really didn't have like any experience at all in the field, right? So Ethernet to me was basically like, okay, everything's Ethernet, yay, and I took it for granted, right? You assume that like every frame looks the same. It looks like what you saw in your CCNA book, but it only does if you're using Ethernet. And then later you learn, oh shit, there's other stuff that's not Ethernet. Now it's not super widely used, but it does exist. Ethernet is not the only like connection technology for networking, right? So either way, there's features about Ethernet that I didn't know about or took for granted as black magic, like auto negotiation. So here we are. But yeah, okay, for anyone new, my name is Trackit Pacer, and I'm a network engineer. I have 4 years of experience doing that. I have an English literature degree, so I didn't do networking at first, and I'm still doing okay. So do with that what you will if you're not in networking, but you're thinking about computer shit. That logo back there that you can see all lit up pretty, it is the logo for a podcast on which I am a regular co-host. It is called The Art of Network Engineering, and you should totally check it out. We're real good, and we're especially real good around the time that I joined, which is like January of this year. So if you want to find it in Apple Podcasts or whatever, go listen to us. They're long episodes. They're about an hour to an hour and a half, but it's a lot of bullshitting and fun stuff. We have a lot of cool guests on where we just talk to them about their journey and how they got into tech. I was a guest once last year in like September. It's a lot of fun, and we have a screaming goat that we play, and we also have a Discord called "It's All About the Journey," and yeah, we're awesome. Basically, is what I'm saying. Okay, enough self plugging. Oh, also, I'm on Twitter, and you can follow me. And that's cool. Okay. Parallel detection. Here we go. I'm going to do it, and I'm going to stop in 15 minutes because my voice is still not used to talking this much. The auto negotiation system includes the ability to work with 10 and 100 megabit per second twisted pair interfaces that don't support auto negotiation. Using a system called parallel detection. The auto negotiation feature was designed after the 10 megabit per second twisted pair media system was developed, and after early 100 megabit per second twisted pair systems were being sold. Because these varieties of twisted pair Ethernet predate the auto negotiation standard, support for the auto negotiation protocol is optional in 10 base T and 100 base TX media systems. Given this history, the standards engineers wanted to include the ability for auto negotiation to work with link partners that don't have auto negotiation support. If auto negotiation exists on only one link partner, and if the media speeds involved include 10 and 100 megabit per second Ethernet, then the auto negotiation protocol uses the parallel detection system to detect certain characteristics of the non-negotiating partner. Didn't know that either. That's pretty cool. But it's only for stuff involving 10 and 100 megabit per second Ethernet. At link initialization time, the absence of fast link pulses from a link partner indicates that the link partner doesn't support auto-negotiation. In that case, if 10 base T normal link pulses are present, the NLPs suffice to pass the 10 base T link integrity test and to enable 10 base T half duplex operation over the link. Although the 100 base TX and 100 base T4 fast Ethernet media systems don't use NLPs, the media signaling characteristics on those systems are sufficiently different to make it possible for parallel detection to determine which media system is in use and to bring up the link appropriately. So it's a pretty smart technology, this Ethernet. Or rather, this auto negotiation. Here we go. Here's the contentious part for me. Auto negotiation supports is required. Auto negotiation support is required on 1000 base TX. I think that might be 1000 base, yeah. On 1000 base TX and 10 gigabase T interfaces to configure essential signal timing characteristics over the link, and it's the only method recognized in the IEEE standard for bringing up those links. Hang on. I don't know the difference between 1000 base T and 1000 base TX, so I'm looking it up. 1000 base T is gigabit Ethernet copper. Okay. 1000 base TX is almost the same as 1000 base T, but it uses 2 pairs of wires instead of 4. And it's not as commonly used as 1000 base T because of the high cost of Cat 6 and sub cable requirements. So 1000 base TX can transmit data at gigabit speeds on Cat 6 and 7 cables, but it's not as commonly used because of the high cost of Category 6 and 7 cables and the falling cost of the 1000 base T products. Interesting. So 1000 base T will use those 4 pairs and 1000 base TX uses 2. Very interesting. Okay. 1000 base T is designed to operate over 4 UTP cable and supports full duplex data transfer, blah, 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 blah. 1000 base TX operated only over 2 of the 4 pairs in the cable. 1000 base TX transmits data at 500 megabits per second on 2 pairs and receives data on the remaining 2 pairs at the same data rate, so that's a gig. In addition, delay skew, which is the difference between the slowest and fastest pairs within a cable, becomes increasingly important as data rates increase. This depends that Cat5 cabling can be used with the 1000 base T standard. Sorry, I just got really dizzy. That was weird. That was weird. I was just reading off the screen. I got super dizzy. Wow, okay. I don't know what that was. Delay skew. The difference between the slowest and fastest pairs within a cable becomes increasingly important as data rates increase. This depends that Cat5 cabling can be used with the 1000 base T standard, but 1000 base TX requires Cat6 cabling. Okay, so basically 1000 base TX seems pretty good, but its cabling is more expensive and 1000 base T is a lot cheaper and people like it better for that reason. But 1000 base TX can be implemented with simpler electronics. This is very interesting. There's not like a clear cut, one is better type of thing. The design of 1000 base TX allows for its electronics to be much less expensive than comparable 1000 base T electronics. So, which is better? It depends on the plan, budget, and application. Okay, so that was an interesting walk down learning lane. Sorry, I'm not feeling great. I'm gonna end the stream. That was super weird. I don't know if I'm just like tired or what, but sorry to end it on this note, but I think I'm gonna have to end the stream. I do not feel good. Thanks for joining me. Sorry it's weird. Ethernet's cool. I stream every Monday night at 6:30 PST or close to that. I really try to stick to that, even if I'm a little late. The issue is just like getting home from work, really. That's all it is. So I hope you can join me every Monday night and occasionally maybe weekends, but so far it's just Mondays. Ethernet's cool. Follow me on Twitter. Follow the Art of Network Engineering. If you want to listen to more shit about network engineering, it's cool. Yeah, it's been fun hanging out. Oh, night otters. How long do you think auto negotiation takes? Sub-second? Oh yeah, it's very fast. Yeah, thanks. Take care, everyone. Yeah, I'm gonna take off. See ya.